Hello everyone. In this lecture, we will discuss the equivalence of three popular principles. So the first principle is called as the induction principle. In this principle, we claim that a subset of a natural number, if it satisfies the two hypotheses, then it is the set of a natural number itself. Now, what are those two hypotheses? So suppose we have subset A of a natural number satisfying that the first element of a natural number, that is 1, is in A, and whenever k is in A, whenever a natural number k is in A, this implies that the k plus 1 is also in A, then A is equal to set of natural number n. Now basically, we see this induction principle whenever we want to prove a statement related to a set of a natural number. We call it as P of n. So all these principles results we use for a natural number, and we put it in this form. So that is the formulation of the theorem that we use in terms of a set of natural number. If it is like, if we want to prove that the result is true for the statement P of n, then in that case what we do, first we prove that it is true for the P of 1 is true, that is by putting n equal to 1 the statement is true. Secondly, what we do, we assume that it is true for k, that is we assume that the statement P of k is true, and we prove that P of k plus 1 is true. And if we succeeded in doing this, then we say that by induction principle the result is true for every natural number. P of n is true for each n. So that's how we have formulated for the set of natural number itself. Okay, so the second statement is the strong induction principle. This is also we have used most of the time. Now here the difference is that instead of, in the second hypothesis, instead of claiming that the result is true for only one k, we say that it is true for all the natural numbers starting from 1 to that k. Okay, and if again it is true for k plus 1, then we claim that it is true for all natural numbers. So when we put it in terms of subset of natural number, so if we have b as a subset of n, and if it satisfies these two conditions, that the first natural number 1 belongs to b, and 1 comma 2 comma dot 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 comma k, if this subset is contained in B, that is 1 is in B, 2 is in B, till k is in B, implies that k plus 1 is also in B, then B is an entire set n. And the third one is a very popular statement in analysis, which we called as an well ordering principle. If we have any subset of a natural number which is non-empty, then the number of element in that set can be listed in increasing order. What it means, that it has a least element. Okay, so we prove that these three principles are equivalent in this lecture. So let's begin with the proof. So in first step we will prove that 1 implies 2. So we will assume that the induction principle is true. So let's assume that the induction principle is true. Okay, so we want to show that the strong induction principle is true. So for that we will begin with any subset of a natural number, and we will assume that it satisfies 1 belongs to B, and it also satisfies 1 comma 2 comma dot dot k is a subset of B implies that k plus 1 belongs to B, and then we need to show that B is equal to n. Okay, so let me start with a subset. Let B be a subset of n, and let it satisfies the first condition, that is 1 belongs to B, and the second condition, that this set 1 2 dot 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 k, if it is a subset of B, then this implies that k plus 1 is in B. So what I need to show is that from here B is equal to n. So for this I'll be using the induction principle. Okay, so now see, the idea is to use induction principle and to show that uh, B is equal to n. We construct a set in such a way that using that I can show that B is equal to n. So what I'll do is that I'll collect all natural number, so it's a subset of n. I'll collect all natural number such that if I collect 1 2 till n, this is a subset of B. Okay, so basically what will happen if I can show that this is itself is equal to n by using, say, the first principle which we have assumed, that is the induction principle, then what will happen if this is equal to n, then all the natural number, if this a is equal to n, then all the natural numbers starting from 1 till all the natural number will also be a subset of B, and so B itself will be equal to n. Okay, so we are doing this so that we know that whenever 1 comma 2 comma k is in B, this also implies that k plus 1 is also in B. Okay, so that's our ultimate claim. So we need to show that this a is equal to n. Okay, so clearly this a is a subset of n. I'll call this a star. Only thing I need to show that n is a subset of a. Okay, so to show that n is a subset of a, we will use this idea. Okay, in fact we use the induction principle to show that a is equal to n. So what we need to show that it is a, to show that a is equal to n, first of all we need to have a subset of n. We already have. We need to show that 1 is in A. Secondly, we need to show that whenever k is in A, that implies that k plus 1 is in A, and that will automatically implies that A is equal to n. So in fact we are not using the standard way of proving that the two sets are equal. We use the induction principle because A is a subset of n on this A. Okay, so now why 1 belongs to A? Okay, so 1 will belongs to A provided the singleton set 1 is a subset of B. Okay, now since we know that 1, this is from the assumption, we have to assume that 1 is in B. So since 1 is in B, obviously the singleton 1 is contained in B, and once the singleton 1 is contained in B, just look at this. So your number is starting from 1 and it is ending at 1 itself, so 1 has to be a part of A. So this would implies that 1 belongs to A. So that's the first hypothesis of induction principle. I'll call this as 1. Okay, now secondly we need to assume let k be greater than 1 and k belongs to A. We need to show that k plus 1 also belongs to A. Once you say that k is in A, the set 1 comma 2 till k is a subset of B as per the definition of A. A is a set of collection of all n such that the element starting from 1 to till n is a subset of B. Okay, so if I say that k is in A, obviously 1 comma 2 till k will be a part of B, and this will definitely implies from our assumption, from this assumption, that is whenever 1 comma 2 comma k is a subset of B, k plus 1 is in B. So B is a set such that it satisfies this two condition. So this would implies that k plus 1 is in B. So once k plus 1 is B, just look at this, 1 comma 2 comma k is obviously a subset of B. Then definitely if I input k plus 1 also, then that 1 2 till k plus 1 will also be a subset of B, as we have already proven that k plus 1 is a part of B. So this would implies that 1 comma 2 comma till k plus 1 will also be a part of B. Once you have an element starting from 1 to k plus 1 is a part of B, then I can say that k plus 1 is a subset of k plus 1 is an element of A by the definition of A. Okay, so this is how we smartly construct the set A, and we keep on using the definition, we keep on uh, using the definition of A, in the straight way or as well as in the reverse way, to use the induction principle to show that A is equal to N. So once k plus 1 is also in A, we started with k in A, we proved that k plus 1 also belongs to A. So this is the second condition of induction principle we have proved, and therefore by induction principle I can say that, in fact, the induction principle is also known as weak induction principle, is the entire set N. So once you say that A is entire set, okay, we will write down, in fact it is clear, but let me write down. Once we know that A is equal to N, we can very easily show that B is also equal to N. So what we know is that, we know that B is a subset of N, right? So now let N be an element of N, then what will happen? N will be in A as A is equal to N, and this would imply that 1 comma 2 comma till N will be a subset of B by the definition of A. So this would mean that what? N is also an element, N also belongs to B. We started with any arbitrary element in N and we proved that it is a element of B. So like this we have proved that N is also a subset of B. So from here I'll call this as double star, and I'll call this as double star, triple star. So from this and this I can conclude that B is equal to N. So in this way we prove that the induction principle implies a strong induction principle, and now in the second step we will show that the strong induction principle implies the well ordering property. So assume that strong induction principle is true. Okay, so that is whenever we have a subset of a natural number satisfying those two conditions, that is one is in A, and whenever k 1 comma 2 comma till k is a subset of k, and k plus, that implies that k plus 1 also belongs to A, then is entire set N. Okay, so we need to show that well ordering principle is true. Let's see what is well ordering principle. So let C be a subset of N and it is non-empty, then this implies that C has a least element. So if I look at this negation, that is if C do not have, C do not have, if C is a subset of N, if C do not have least element, then the only possibility for C is that it has to be empty. Okay, so this is like an hypothesis, and if it is non-empty, then it implies that it has a least element. So we prove it in a contrapositive way. Okay, so what I'll do is that I'll start with any subset of N. Okay, and I'll say that it do not have a least element. Okay, so we prove the contrapositive of the statement. So what I should have is that we need to show that the only possibility for C is that it is empty. Okay, so claim C is empty. So if I look at again the contrapositive of this, that if C is non-empty and if it is a subset of n, then C should have the least element. Okay, so we prove it in this way using contrapositive. Okay, now what we have in hand is the strong induction principle. So we can only construct, so in that case we can construct a set to show that C is empty. So what I'll do is that I'll construct a set S which is a complement of which is a subset of n and it's a complement of C. So I'll take it as n difference C. Okay, so it's n difference C, so definitely it's a subset of n. Okay, so if I call it as n difference C, then see, our aim is to show that C is empty. So first of all, you can very easily say that 1 is not a element of C, because if 1 is an element of C, then 1 itself is the least element of C, right? But you are saying that C do not have a least element, so least element of C. So therefore 1 is not a element of C. Okay. So if 1 is not in C, then definitely, since S is n difference C, so it's a what I can say that S is a set of all natural number which is not in C. So in fact what I'll show is that if I can show that S itself is equal to n, S is a set of all natural number, then that will automatically implies that C has to be empty set. Okay, because if S is equal to n, then and if I say that S is n difference C, then definitely C has to be an empty set. So that's the idea. So I'll show that S is equal to n by the strong induction principle. Okay, so from here we have already shown that 1 is in S, so that proves the first part of strong induction principle. Now to prove the second part of induction principle, to show that S is equal to n, we are applying it on this S, we are applying the strong induction principle on this S. Okay, what I'll have to assume is that I'll have to assume that there is a natural number which is greater than n, such that S contains 1 to till that natural number. Say suppose k is greater than or equal to 1 and all the elements starting from 1 to till k is a subset of S. This is what we have. Okay, then I need to show that k plus 1 is also in S. So if I can show that by strong induction principle, we are done. We have shown, we can conclude that S is equal to n, and that immediately will say that C has to be an empty set. Okay, so once I say that all this 1 to till k is an element of S, then definitely it is not a part of C. So none of this element will be a part of C. So this would implies that no element, that is 1 2 till k, is an part of C. So I can say that X do not belongs to C for all X equal to, or for X equal to 1 2 till k. Okay. So now I need to show that k plus 1 is an element of S, that I can show by that I can prove by showing that k plus 1 is not an element of C. Now what will happen, why it is not an element of C? If k plus 1 is an element of C, then it's already do not contain 1 2 till k. So k plus 1 is going to be the first least element in that C. But by our assumption, we are saying that C do not have any least element. So that will rule out the case that k plus 1 is a part of C. Okay, so now if I say that k plus 1 is an element of C, then this would implies that k plus 1 is the least element of C. Least element of C. Okay, that's a contradiction, so we cannot have this. Therefore k plus 1 do not belongs to C. Once it is not in C, the way we have constructed S, it has to be a part of S. So now what we have shown is that whenever 1 2 till k, whenever a set containing this k element is a subset of k, and k plus 1 is also that this implies that k plus 1 is also an element of S, then this satisfies the second hypothesis of strong induction principle, and therefore S has to be equal to N. Okay, so this is, so in fact we have proved thus 1 comma 2 dot 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 till k, whenever it's a subset of S, we have proved that k plus 1 is an element of S, right? This is the second property or the second hypothesis of strong induction principle, and therefore I can say that S is equal to N by strong induction principle, that is by our assumption. Okay, and so once C is equal to N, this would automatically implies that C is an empty set. So by contrapositive we have shown that if C is non-empty and it's a subset of N, then it has to have least element, hence the claim. Okay, now the last one, 3 implies 1. So here we assume that the well ordering principle is true. Assume that well ordering principle is true. So basically what we are assuming that if we have any subset of a natural number which is non-empty, then it has to have the least element. Okay, now we need to show the first one, that is we need to show that the induction principle is true. Okay, so for that we need to start with any subset of N satisfying the first two condition of or the first two hypotheses of induction principles. I'll simply write satisfying. We know what are those hypotheses. The first hypothesis is that 1 is in A, and whenever k is in A implies k plus 1 is in A, then this should imply that A is equal to N. So satisfying the hypothesis of induction principle. Okay, so we need to show that A is equal to N. Okay, so first, if A is not equal to N, then what? So if A is not equal to N, then definitely if I construct a set N difference A, by the way N is bigger than A because A is a subset of N. So if I construct a set N difference A, this is going to be non-empty because A is not equal to N. Okay, so this is non-empty. It's a non-empty subset of N. So once it's a non-empty subset of N, by well ordering principle, this should have least element. Okay, so therefore C has the least element. By well ordering principle. Okay, so let me call it as, say, small l. So now if L, since L belongs to C and C is n difference A, L will not be a part of A, right? Okay. Now you know that there is already one element in A for sure, that is 1. Therefore L cannot be equal to 1. Okay. So therefore L will not be equal to 1 as 1 is in A. Okay. I mean, there might be some more elements in A as well, but we are sure that 1 by the first hypothesis of strong induction principle, we know that 1 is in A, and that least element L, it's a least element of C. So by the definition of C, L is not a part of A, and therefore by any chance L will never be equal to 1. Okay. So if L is not equal to 1, then definitely L has to be greater than or equal to 2, right? So if L is greater than or equal to 2, then L minus 1 will be greater than or equal to 1. This would implies that L minus 1 is a natural number, right? I mean, it's simply a natural number. It starts from 1 onwards. Okay. By the way, L minus 1 is a natural number, because by the construction over here it can take 1, or it can take a natural number which is greater than 1, because L is a natural number. Okay. Now just look at this. Since L is a least in C, this would imply that any element which is lesser than this L will not be part of C. So this would imply that L minus 1 will not be a part of C. So if L minus 1 is not a part of C, just look at the definition of the way C is defined. C is n difference A. So if any element is not in C, then definitely it has to be in A. So this would imply that L minus 1. That's a definition of a complement of a set with respect to the universal set. Okay. So if L minus 1 is in A, this would imply that, because we know that, see here, this is like K is in A. So if K is in A, by the second hypothesis of induction, K plus 1 is also in A. This is by hypothesis 2. This is the second hypothesis of induction principle. This implies that L belongs to A. Isn't it a contradiction? So if L is in A, L is not in C. Again, you just need to know how to roll out your definition, or how to look at the definition in such a way that you can keep on using to get your tasks. You need to show that our assumption that A is not equal to N is not true. So we need to get somewhere at some stage a contradiction. So this is the contradiction that we are getting, and that too using the well ordering principle. And so this contradiction states that the only possibility for A is the whole set N. Okay. So with this we have proved that all the three principles which we have studied as an induction principles are true, okay, are equivalent. Okay. So with this I end up this session. In the next lecture we will see some lectures on the well ordering. We will see some lecture on the partial ordered set. Okay. uh, that is the order relations. Thank you for watching this, and have a nice day ahead.